Okay, so this video will be a condensed lecture on matrix operations, namely matrix addition and subtraction, scalar multiplication, and the most interesting operation being matrix multiplication. Let's start with matrix addition. If I consider this matrix, say 1, 2, 3, 9, plus the matrix, say -5, 6, 7, -1, well, this is a 2 by 2 matrix, 2 rows, 2 columns. This is a 2 by 2 matrix, 2 rows, 2 columns. When we add matrices that are of the same size, the new matrix is of the same size, and we simply add corresponding entries. So if you want this entry right here, you simply do 1 plus -5, which is -4. If you want the entry here, 2 plus 6, +8. If you want the entry here, 3 plus 7, +10. And if you want the entry here, 9 plus -1, +8. And this is how you add matrices. What about subtracting matrices? Let's consider the next example. Let's go with 0, 8, -11, 5, 6, -2, minus 1, 1, 3, -2, 1, 1 equals, well, both are 2 by 3 matrices, 2 rows, 3 columns. So the result would be a 2 by 3 matrix as well. And if we add corresponding entries, we will then subtract corresponding entries. So two rows, 3 columns. So the entry here is 0, -1, -1. The entry here, 8, -1, +7. The entry here, -11, -3, -14. Let's keep going. The entry here, 5, minus -2, 5 plus 2 is 7. The entry here, 6 minus 1, 5. And finally the entry here, -2, -1, -3. And this is how you add and subtract matrices. One thing that is worth mentioning is they have to be of the same size. You can only add or subtract matrices of the same size. So for example, if you asked, well, what about this? 1, 2, 3, 5 plus 8, 9, 6, 5, 1, 0. And you ask, well, what is the result of this sum? And the answer is it is not defined, as the first is a 2 by 2 matrix, the second is a 3 by 2 matrix. If you think of it, well, if we're going to add corresponding entries, we would add 1 with 8, 2 with 9, 3 with 6, 5 with 5, but there's nothing here to add to this row. And so when you add matrices or try to add or subtract matrices of a different size, the result is simply not defined. It does not exist. And that takes care of matrix addition and matrix subtraction. What about scalar multiplication? Multiplying a matrix by a real number. As you will see, this is also a very simple operation. So what if I looked at, say, 4 times the matrix 1, -2, 3, 3, 9, -7? Well, as you can probably guess, this is a 3 by 2 matrix. The result will be of the same size, still a 3 by 2 matrix. And we obtain the new entries of this matrix by multiplying every single entry of the original matrix by the real number. So we'll have 4 times 1, 4. 4 times -2, -8. 4 times 3, 12. 4 times 3, 12. 4 times 9, 36. 4 times -7, -28. And that's it. This is scalar multiplication, multiplying a matrix by a real number. This operation always exists. given any matrix and any real number, you can always multiply the matrix by the real number by multiplying every one of its entries by the given real number. We could look at one last example, say negative 3 times the matrix 1, 2, 3, 4. And we would get again a 2 by 2 matrix. The entry here, negative 3 times 1, negative 3. The entry here, negative 3 times 2, negative 6. The entry here, negative 3 times 3, negative 9. And the entry here, negative 3 times 4, negative 12. And that's it. And that is scalar multiplication. Multiplying a matrix by a real number by multiplying all of its entries by the given real number. So as you can see, matrix addition, subtraction, very simple. Scalar multiplication, very simple. Now, much more interestingly, is matrix multiplication. Can we multiply two matrices together? The answer is yes, some of the time. Let's start with very simple matrices. We'll look at a row times a column matrix. So if I looked at the matrix, say 1, negative 5, times the matrix 8, negative 7, this is called a row matrix of length 2, as it is a single row with two entries. This is called a column matrix of length 2, as it is a single column with two entries. Look at the size of these matrices. This is a 1 by 2 matrix. This is a 2 by 1 matrix. And the only way to have a defined multiplication is for the column index of the first matrix to equal the row index of the second matrix. If those two are equal, the new matrix will be a 1, in this case, by 1 matrix, which for us is just a real number. And you can ask, well, how do we multiply a row times a column? The idea is, and this is a bit more subtle, but you will understand very shortly after we look back to linear systems, but we multiply corresponding entries and we add them up. So first entry of the row times first entry of the column plus second entry of the row times second entry of the column. And that's it. So we multiply corresponding entries and we add them up. So first with first, second with second, and we'll give an example where we have more entries and we keep going, and we add all of these products. So here we would get 8 plus 35, which gives us 43. So this row times this column is the real number 43. Let's go with a row and column of length, say 4. So negative 1, 2, negative 3, 4 times 0, 5, 6, negative 1. This is a 1 by 4 matrix. This is a 4 by 1 matrix. So once again, 4 equals 4. The product is defined, and the result will be a 1 by 1 matrix, which is a real number. As we have just discussed, we simply multiply corresponding entries and add them up. So negative 1 times 0 plus 2 times 5 plus negative 3 times 6 and finally plus 4 times negative 1. And let's compute. So we'll get here 0 plus 10 minus 18, this is a plus, minus 4, 10 minus 18, negative 8, negative 4, negative 12. Once again, a real number, a 1 by 1 matrix. What if we tried, and you'll see quite easily, to multiply a row times a column matrix of different lengths? Well, the result will simply be undefined. So if we tried, say, 1, 9, 8, 7 times 6, 5, negative 4, you see, could we perform this multiplication? Well, if you look, this is a 1 by 4 matrix, 1 row, 4 columns. This is a 3 by 1 matrix, 3 rows, 1 column. And as you can see, 4 is not equal to 3. And so the product is undefined, or simply not defined. This does not exist. And again, think of why. How do we multiply a row times a column matrix? We multiply corresponding entries and add them up. So if you try this here, you'd multiply 1 with 6, plus 9 with 5, plus 8 with negative 4, plus 7 with, and there's a missing entry. So it is impossible to multiply corresponding entries if you don't have the same number of entries. And so you can only multiply a row times a column matrix if they have the same number of entries. Now, the question is, well, what if we have more general matrices, not just a single row times a single column, but an arbitrary rectangular times an arbitrary rectangular matrix? When is the product defined? And if so, how does it work? Well, let's see. Let's start with a very simple example. Two 2 by 2 matrices. So we start with 1, 2, 3, 4 times, say, negative 2, 3, 5, 1. If you look, this is a 2 by 2 matrix. This is a 2 by 2 matrix. The number of columns of the first equals the number of rows of the second. So here multiplication will be defined. And the new matrix will be a size 2 by 2 matrix. Or actually, let me take up a little bit more space to really show you how we'll compute the entries of this matrix. This is the entry, if you think of it, in the first row, first column. And so we take the first row of the first matrix times the first column of the second matrix. And so we do 1 times negative 2 plus 2 times 5. And now we have the first entry of our product. The entry here, if you think of it, now we are in row 1, column 2. And so we take the first row of the first matrix and the second column of the second matrix, and we multiply them together. So we'll have 1 times 3 plus 2 times 1. There you go. We now have constructed the first row of our new matrix. If you want the second row, this is the entry in row 2, column 1, so 2, 1. So we take the second row of the first matrix times the first column of the second matrix, row 2, column 1. So 3 times negative 2 plus 4 times positive 5. And finally, the entry in row 2, column 2, so 2, 2. So we take the second row of the first matrix times the second column of the second matrix. And so we get 3 times 3 plus 4 times 1. And so there you have it. So let's compute these entries. We have negative 2 plus 10, positive 8. 3 plus 2, positive 5. Negative 6 plus 20, positive 14. 9 plus 4, 13. And there you have it. This matrix times this one equals this one. Let's call this matrix A. Let's call this matrix B. And this, of course, is the matrix AB. Just for fun, let us now compute B times A. And one thing that's worth mentioning too, to make our future calculations more efficient, is to realize that to construct the first row of AB, we simply fixed the first row of A and went through every column of B. You see, we fixed the first row of A, we will construct the first row of AB, and we go through every column to construct the entries. So if you look, fix the first row, negative 2 plus 10, 8. 3 plus 2, 5. And now we will construct the second row by fixing the second row of our first matrix A and going through every column. Negative 6 plus 20, 14, 9 plus 4, 13. So every time from now on that you construct a product of two matrices, always fix the first row of the first matrix, go through every column of the second matrix, and this will allow you to construct the first row of your new matrix, AB. To construct the second row, fix the second row of your first matrix A, go through every column of the second matrix, and this will allow you to construct the second row of the new matrix AB. If there were additional rows, we would just keep going like this. But just for fun now, let's compute B times A and see if we notice something interesting. So negative 2, 3, 5, 1 times the matrix 1, 2, 3, 4. So once again, there are two 2 by 2 matrices. So 2 equals 2. The product is defined. And the result will be a 2 by 2 matrix. And then we can find the entries much quicker. As we've said, we will construct the matrix BA. Right, this is matrix B times A. One row at a time. To build the first row, fix the first row of the first matrix, and go through every column of the second. So negative 2 plus 9, 7. Negative 4 plus 12, 8. To construct now the second row of BA, we of course now fix the second row of the first matrix B and go through every column. 5 plus 3, 8. 10 plus 4, 14. And that's it. So it's really efficient. And if you notice, something really interesting has happened here. AB and BA are not equal. And so you have to be very careful when it comes to matrix multiplication. In general, AB and BA will not be the same matrix. And you see, it's not like they're close to be the same. They're really, really far off from being the same. And so in general, keep this in mind. AB and BA will be different matrices. Let's look at a few more examples of matrix multiplication. We've multiplied two 2 by 2 matrices. Let's multiply now rectangular matrices. A 2 by 2 is a square matrix, as they have the same number of rows and columns. Let's go through one more example. Suppose we take the matrix A to be 1, 2, 3, negative 2, 1, 5, and matrix B to be, say, negative 4, 8, 1, 1, negative 1, 2. Let's see if we can compute AB and BA, and once again see if they are the same or different. Let's look at AB first. So matrix A, 1, 2, 3, negative 2, 1, 5, times matrix B, which is negative 4, 8, 1, 1, negative 1, 2. First, is this defined? Well, this is a 2 by 3 matrix. This is now a 3 by 2 matrix. So 3 equals 3. So we have a defined multiplication, and the new matrix AB will be a 2 by 2 matrix. So a nice little square matrix. And once again, always construct your new matrix one row at a time. Fix the first row of the first matrix and go through the columns of the second. So we'll have here negative 4 plus 2, negative 2, negative 3, negative 5. Then we'll have 8 plus 2, 10, plus 6, 16. So we have the first row of AB. To construct the second row, fix the second row of the first matrix. So forget these for now. We'll have now going through every column, we'll construct the second row of AB. So we'll have positive 8 plus 1, 9, minus 5, 4. Negative 16 plus 1, negative 15, plus 10, negative 5. And then we have matrix AB, which is a nice little square matrix, a 2 by 2 matrix. Let us compute now b times a. Matrix B is right here. So negative 4, 8, 1, 1, negative 1, 2, times matrix A, 1, 2, 3, negative 2, 1, 5. First, is the multiplication defined? Well, this is a 3 by 2 matrix. This is a 2 by 3 matrix, so 2 equals 2. Multiplication is defined. And the new matrix will now be not a 2 by 2 as AB, but now a 3 by 3 square matrix. So it will be bigger. But as always, one thing is worth noting, clearly AB and BA won't be the same. They don't even have the same size. As always, when you construct a new matrix as a product between two matrices, you construct it one row at a time. So to construct the first row of BA, we fix the first row of B, go through every column of A. So we'll have negative 4 plus negative 16, negative 20. Then negative 8 plus 8, 0. Then negative 12 plus 40, 28. To construct the second row of BA, we now fix the second row of B, 1, 1. And we go through again every column of A to construct the second row of BA. So we have 1 minus 2, negative 1. 2 plus 1, 3. 3 plus 5, 8. And there you go. Done. And to construct the third row of BA, we fix the third row of B and go through once again every column of A. Negative 1, negative 4, negative 5. Negative 2 plus 2, 0. Negative 3 plus 10, positive 7. And so there you have it. Here's AB, here's BA. And once again, clearly, they are different matrices. So always keep this in mind. In general, multiplication does not commute. A times B will not always be B times A. Let's look at one last example where multiplication will not be defined. So what if we try and do the following? What if we take and we try and do A times A? So multiply A with itself. Well, this is a 1, 2, 3, negative 2, 1, 5 times 1, 2, 3, negative 2, 1, 5. Well, let's see. A is a 2 by 3 matrix, 2 by 3 matrix, and 3 is not equal to 2. The number of columns of the first matrix is not the number of rows of the second, and so this multiplication of A and A actually does not exist. It is not defined. And think of why this is clear. Suppose you tried to perform this multiplication. Well, you would do a row times a column. Pick any row of the first matrix, any column of the second. Can you multiply such a row by such a column? The answer is no, because we multiply a row times a column by multiplying corresponding entries and adding them up. But you can't multiply corresponding entries if you don't have the same number of entries. Here you would do 1 times 2 plus 2 times 1 plus 3 times. There's something missing. And that's why the multiplication of A and A is not defined. The number of columns of the first matrix, 1, 2, 3, must equal the number of rows of the second, 1, 2. If they are not the same, the product does not exist, and that's the end of it. And that's it. So this is how you compute matrix addition, subtraction, scalar multiplication, and multiplication between two matrices. Our concluding remark is the following. Whenever you handle matrices algebraically, they behave just like real numbers. With respect to addition, subtraction, multiplication, and scalar multiplication, you can treat matrices as if you were dealing with real numbers, except for two exceptions. One that we have already seen two examples of. In general, this is a word of caution. So caution number one, in general, a times b will not equal b times a. Clearly, if a equals b and aa is defined, then you'll have aa equals aa. That clearly is equal to each other. But in general, ab is not equal to ba. So always be really, really careful about this property. This is true of real numbers, no longer true in general for matrices. Number two, if you remember, as long as you had a non-zero real number, so suppose A is not the zero matrix, the matrix where all of the entries are zero, and suppose that you had A times B was equal to A times C. Now if these were real numbers, if A, B, C were real numbers and A was not the zero real number, we can cancel A and imply that B must be equal to C. This is also not always true of matrices. A could not be the zero matrix. AB could be equal to AC, and yet B and C could be different. So the fact that A is not the zero matrix and that AB equals AC does not imply, this arrow means imply, we'll put a slash across it. So even though A is not the zero matrix and AB equals AC, it does not imply that B is necessarily equal to C. And those are the two big exceptions when it comes to matrix operations. So always be really careful when you handle matrices algebraically. Treat them as if you had real numbers, except for these two exceptions. Let me give you a really short example of the second statement that is not always true of matrices. We'll take very simple 2 by 2 matrices. So the assumptions are that A must not be the zero matrix. So take A to be 1, 0, 1, 0. These two entries are not 0, so this is not the zero matrix. Let's take the matrix B to be 1, 5, 3, 4, and matrix C to be, say, 1, 5, 8, 9. Clearly, B is not equal to C. This entry is not this one, this entry is not this one. So we have the two assumptions. A is not the zero matrix, B is not equal to C. Let's look at AB and AC. This is a 2 by 2 matrix. This is a 2 by 2 matrix. 2 equals 2. And the result is a 2 by 2 matrix. As always, we construct the entries of our new matrix one row at a time. Fix the first row of A, go through the columns, you'll get 1 plus 0, 1, 5 plus 0, 5. Second row, same thing. 1 plus 0, 1, 5 plus 0, 5. And this is AB. Let us now compute AC. Same argument as before, both are 2 by 2 matrices. The result will be a 2 by 2 matrix. Fix the first row of A, go through the columns of C. 1 plus 0, 1, 5 plus 0, 5. Second row of A. 1 plus 0, 1, 5 plus 0, 5. And you can see clearly that AB and AC are equal. And so you see, A is not the zero matrix, AB is equal to AC, and yet B is not equal to C. So you have to be very careful if you ever have that AB equals AC. You can't always just say, well, A is not the zero matrix, so I can just cancel A, therefore B equals C. this actually fails for matrices. And this is a beautiful example of this statement. We will very shortly see what it what does it take for a matrix to allow us to cancel it from a multiplication. But right now this is a big no-no. It's not because that AB equals AC that you can automatically say that B equals C. So keep that in mind. And that's it.